All right, let's take a look at this proof. The theorem we're going to prove here is that the limit, or that if f is a differentiable function at a, then f is continuous at a. Okay, so that's the goal here we're going to try to prove. Now, first thing to notice about a proof is the way it's written. This is an essay. This is way more like an essay from English class than it is from most of the math from high school. What I start out by doing is I start out telling the reader what I'm going to do. It says, then f is continuous. That's what I need to show. So, I tell the reader, to show f is continuous at a, it must be shown that, and I write down the definition of continuity. This is what it means to be continuous at a. It's the definition. The limit as x approaches a of f of x equals f of a. So I start off, notice the English sentence, and that would be required. This is the way it's written. Proofs are always written in complete sentences. You might call it a mathematical sentence, capital letter, period at the end of the equation, right? It's one long sentence. Okay? You might call it a mathematical sentence because there's a big formula in the middle, but regardless, still a sentence. Now that I've told you what I'm going to do, now I tell the reader what I know. If f is differentiable at a. Okay? So, since f is differentiable at a, what does it mean? It means the derivative, which is f prime of a, and this is the definition of the derivative right here. The limit as h approaches 0, f of a plus h minus f of a over h. That's the definition of the derivative at a. To be differentiable, all it means is that that derivative exists. That's all I know. I have no idea what it is. I have no idea what the function is. All I know is that derivative, that limit, exists. Now, for this particular proof, we're actually going to use this alternative way of writing the derivative. This is often the one that's introduced first when you're learning the derivative for the first time, because it's actually rise over run. y2 minus y1 over x2 minus x1. It's actually a slope when you're letting the distance between the 2 points go to 0. But this is exactly the same thing. It's just take x minus a to equal h. Okay, so if you hadn't seen one of these before, that's the only difference. So all I know is that that limit, both these are the same limit, that limit exists. And I need to show this. All right, so if I'm going to show this, I'm going to start at the left-hand side, and by logical step-by-step process, make my way to the right-hand side. I need to show that the left-hand side here does in fact equal the right-hand side. So, I start with the left-hand side. The left-hand side, limit as x approaches a of f of x, and I need to show that thing equals f of a. Now, somewhere along the way, I'm going to use the fact that this limit exists. Again, these two are the same. We're going to use this one here, just because there is a way to do it with this one, but I'm going to use this one. It's just there's a couple different ways to do it, but this is I think the easier way. And so what I'm going to do is I'm going to start with this, again, the left-hand side, and I need to produce this. I need to build this. I need to make this thing show up. And so look, I've got an f of x there. I've got a limit of x as x approaches a, and I've got an f of x. I'm going to start by building the top. I'm going to subtract f of a. So here it is, f of x minus f of a. Now, of course, in order to do that, in order to keep things equal, I better add f of a as well. So you can see that these two actually cancel each other out, and I just get f of x, right? But I'm unsimplifying it in a sense, right? I'm putting the f of a in there, plus n minus f of a, in order to create the top here, f of x minus f of a. Okay? So now, I've got a limit of f of a plus this thing that I want. So I'm going to separate the limit using a limit law to be the limit of the first chunk, f of a, plus the limit of the second chunk, the chunk that I'm interested in. Okay? Now again, the way limit laws work, that only works, you're only allowed to do that if both these limits exist. So let's take a look at the first one. Does that limit exist? The limit of f of a as x approaches a. Well, that looks a little weird because it's normally f of x. There's no x's left in here, right? What does f of a mean? It means take every x in f and replace it with a. So there's no x's in here. This has no x's. So x can do whatever the heck it wants. Let x go to 17, let x go to 10 billion, it doesn't matter. This is always staying as f of a. It's like the limit of 5 as x approaches whatever. Well, 5 is 5. It'll always be 5. X can do whatever the heck it wants. It'll always be 5. Okay? So that limit certainly exists. It's just a limit of a constant. On the other side, I got the limit of f of x minus f of a. Again, that's the top of the fraction I want. Well, again, now I need to create the bottom. So I'm going to multiply and divide by x minus a. Now I'm allowed to do that because I'm only looking at the limit as x approaches a. I don't care what happens when x equals a. When x equals a, this is 0 and this is 0, and I've multiplied and divided by 0, and I'm not allowed to do that. But around x is a, these are not equal to 0, and I can multiply and divide by them. Next step, I then pull the limit through the brackets. I've got the limit of the first fraction times the limit of the second function. So I bring the limit through with a limit law. Limit of a product is product of the limits. And now look what I've got. I've got this limit all off by itself. That's exactly what I wanted. That's exactly what I was trying to produce. That was the whole reason I added and subtracted f of a, the whole reason I multiplied and divided by x minus a, to get that limit by itself. Now again, when I did that limit law is only justified assuming that both limits I separated to exist. Well, let's take a look at this one. The limit of x minus a as x approaches a. That's actually really easy. X minus a, that's a polynomial in x. As x approaches a, so this is like x minus 3 as x approaches 3. Really easy. Just plug it in. Polynomials, you can find the limit just by plugging it in. So I plug in a minus a, that one's 0. And this limit, as I said, is exactly what I produced. It's f prime of a, and all I know is it exists. And that's actually exactly what I needed. In order to justify the limit law, I needed that to exist. So all the limits existed, which justified all the limit law breaking up. And I'm down to this. F of a, the limit as x approaches a of f of x equals f of a plus f prime of a times 0. Well, what's f prime of a times 0? 0. Doesn't matter what f prime is. F prime of a times 0 is 0. So all I'm left with is f of a, which is exactly what I needed to show. See how smooth that is? Now when you're looking at this, you've got to look at this as one long line of equations. This thing equals this thing, which equals this thing, which equals this thing, which equals this thing. You're not going back to this. This is you could write this whole thing on one long line. This equals this equals this equals this equals this equals this equals this. And so you're reading it on one long line. This thing through all those equal signs equals this. And so I've proven exactly what I said I was going to prove. The limit as x approaches a of f of x equals f of a. And so that completes the theorem. I've taken that f is differentiable, the fact that this thing exists, and I've proven the definition of continuity, that limit as x approaches a of f of x equals f of a. The only last thing we do is very commonly for a proof, we'll put a little box at the end. This is indicating to the reader that the proof is done. Hope you found that helpful.